Hi everyone, it's Bea again. Welcome to the first lesson for our unit about exponential and logarithmic functions. In this unit, we'll learn all about how these functions behave and use them to solve some very interesting problems. Let's dive in. On the cover sheet of your PDF, you had this pre-video activity. If you haven't had a chance to work on it yet, pause the video to do that now. Now, let's work it out together. The problem reads, Jake opens a savings account with an initial deposit of $50. His account will continuously earn interest, doubling his balance at the end of each year. Describe a function that models Jake's account balance over time by using a table and a graph. Make sure to label the axes. When modeling real-world situations with functions, it's important that we first identify the input and the output. Inputs are always placed on the left column of the table and on the x-axis, and outputs go on the right column of the table and y-axis. We want to model the balance in Jake's account, so the balance must be the output of the function. Since this balance depends on the time passed, the number of years is the input. Now let's fill up our table. Jake made an initial deposit of $50, so at 0 years, he just had those $50. Every year, his balance will double, so 1 year after, there will be twice as much money, that is, $100. Continuing this pattern, after 2 years, he has $200, after 3 years, $400, and after 4 years, $800. We can use these points to draw the graph. On our x-axis, it makes sense to go by ones. But on our y-axis, we'll have bigger quantities, so let's go by 50s. Plotting these points and then connecting them, we get this curve. Let's move on to the guided notes and continue analyzing Jake's function with a new question. How much money will he have after 5 years? After 10 years? After X years? Here's our table from before. Pause the video now and try to answer these questions yourself. Then we'll work them out together. To find the balance after 5 years, we could use year 4 and increase 1 more year by doubling the 800, which gives us 1600. To find the balance after 10 years, one approach would be to continue our table until we reach year 10. If you worked it out this way, that's great. But let's try to see if there's a more efficient way to get there without having to go through years 6 to 9. Let's look back at year 5. Could we have gotten the balance without knowing years 1 to 4? We started with 50 and then multiplied by 2 5 times over a total increase of 5 years. How can we express these multiplications as a single operation that takes us directly from year 0 to year 5? Well, multiplying by 2 5 times is the same as multiplying by 2 to the power of 5. So the balance can be written as 50 times 2 to the power of 5. Could we use this perspective to quickly find the balance after 10 years? If over an increase of 5 years, we had to multiply 50 by 2 5 times, after 10 years, we should multiply 50 by 2 10 times. The balance at year 10 is simply 50 times 2 to the power of 10. This expression is equal to $51,200. But let's keep the answer in this form since it might help us with the next question. Now we need to find the balance after X years. If you weren't able to answer this question before, pause the video and try again now. Without having a specific value for X, it's impossible to find a specific dollar amount. However, Notice how the exponent of the 2 from the previous balances is simply the number of years. So, after x years, the balance would be this same expression but with an x as the exponent. That is, 50 times 2 to the power of x. This expression actually gives us the equation for this function. Let's name the function j and let x be the number of years. Then j of x represents Jake's account balance, and it is equal to 50 times 2 to the power of x. The 50 represents the initial balance, and the 2 is the number we multiplied the balance by every year, which is actually called the growth factor. Do you remember what we call these functions where the variable is an exponent? We call them exponential functions. Exponential functions are functions that have a constant growth factor, which means that every time the input increases by 1, the output is multiplied by the same number, called the growth factor. In this particular scenario, that's exactly what happened. For every increase of 1 in the years, the balance was multiplied by 2. Here's a second question about Jake's account. How long will it take for the account to reach $3,200? Pause the video now and try to solve this problem yourself. Here we want to find the time given a particular balance. Now that we have an equation for the balance, let's take it for a spin. Since j of x represents the balance, we can replace it with 3,200 and then solve for x, which represents the time we're looking for. We can't multiply the 50 with the 2 due to the order of operations, so let's divide both sides by 50. We get 64 equals 2 to the x, so we ask ourselves, 2 to the power of what is 64? The number of times we multiply 2 to get 64 is 6, so the solution to our equation is x equals 6. We can confirm this with our table by taking year 5 and increasing by 1 more year, which doubles the 1,600 and results in the 3,200 we needed. Therefore, it would take 6 years for the account to reach $3,200. Let's look at one last question about Jake's account. How long will it take for the account to reach $4,000? This question is very similar to the previous one. We're being asked for the time given the balance. Once again, we can replace j of x with 4,000 and divide both sides by 50. We get 80 equals 2 to the power of x. So we need to find what power of 2 gives us 80. Well, from the previous question, I remember 2 to the 6th power is 64, but then 2 to the 7th power goes all the way up to 128. I see you wondering, Mia, is there an exponent that can turn 2 into 80? Let's see. Since 80 is between 64 and 128, the exponent we need to get 80 should be somewhere between 6 and 7, and closer to 6 than to 7, since 80 is closer to 64 than to 128. Pause the video and using a calculator, try some decimal values between 6 and 7 to find an exponent that will get us to 80, or at least really close to it. Trying out some numbers with the calculator, we can figure out that the exponent must be more than 6.3, but less than 6.4. And after a lot of trial and error, we would eventually see the exponent is around 6.3219, and a bunch of other numbers. But we never quite get exactly 80. Does this exponent even exist? Yes, it does. The exact exponent that will turn 2 into 80 is called the logarithm base 2 of 80, or log base 2 of 80. If we raise 2 to the power of log base 2 of 80, we get exactly 80. Therefore, the exact number of years it would take for this account to reach $4,000 is log base 2 of 80. If we input this log into a graphing calculator, such as Desmos or GeoGebra, we would see that this number is in fact approximately equal to 6.321928 years. But we would have never been able to write the full decimal expansion because this number is irrational, which means it has an infinite non-repeating decimal representation. In later lessons, we will practice approximating logs with the calculator, but for now, you only need to be able to write the exact solutions with logarithms. Let's officially define what a logarithm is as follows. The logarithm base b of x, or log base b of x, is the exponent to which we need to raise b to get x. So in general, b to the power of log base b of x is, by definition, equal to x. For example, how would you express the exponent that turns 5 into 6? That would be log base 5 of 6. We always need two numbers to express a logarithm, a base and an argument. In the case of log base 5 of 6, the base is 5 and the argument is 6. As we wrap up our lesson today, let's use logarithms to solve a couple equations. Our first equation is 3 to the power of x equals 8. Here, x needs to be the exponent that turns 3 into 8. So x is equal to the logarithm base 3 of 8, since we know that 3 to the power of log base 3 of 8 equals 8. Now, try this second equation on your own. 1.1 equals 7 to the power of x. Pause the video and try it out. Similarly, we need x to be the exponent that turns 7 into 1.1. So, x equals log base 7 of 1.1, because we know that 7 to the power of log base 7 of 1.1 equals 1.1. Notice how we needed logarithms for these equations, since 8 is not a nice integer power of 3, such as 9 or 27, and neither is 1.1 a recognizable integer power of 7. Today, we learned two very important concepts we'll be using throughout this entire unit. First, we saw that exponential functions are those that have a constant growth factor, which means that every time the input increases by 1, the output is multiplied by the same number. And second, the logarithm base b of x, or log base b of x, is the exponent to which we need to raise a base b to get the argument x. Throughout this unit, we will learn how exponential functions can model the cooling of food, population growth, and radioactive decay. By the end of this unit, you'll be able to write, analyze, and graph both exponential and logarithmic functions, and solve all kinds of exponential and logarithmic equations. Get ready for a bunch of awesome and interesting math! Once you've finished your guided notes, complete the additional practice in your PDF. After that, make sure to complete the online practice. See you next time! Hey, hey.